Hello and good afternoon, everyone. Welcome to our presentation on hijacking marine autopilots. Alrighty, let's start off with a video. This is a chart plotter that's updating an autopilot and what looks to be a very simple and routine update process. However, that's not the case here. And that's what we are going to show you through this presentation.
Alrighty, for those familiar with CAN data, what we have is the upgrade happening over the CAN network, sending all this data to the autopilot, which is a malicious firmware update. At this point, the autopilot then takes the update and reboots, and then it starts sending out what's called address claims. This is something we'll talk about a little bit more later if you're not familiar with CAN, but essentially we are taking control over the engine controller on the network. So this research and what you'll see here, we wanted to follow a responsible disclosure process. Obviously, we want to be ethical hackers, improve the cybersecurity industry and the maritime industry. We don't want to harm them. So what we did once we discovered some of these things here was inform the manufacturer of this directly, shared a PowerPoint of these findings, and we also asked them if they had a vulnerability reporting system, and unfortunately they did not. So what we did is proceeded to submit information to MITRE to request a CVE ID. We did this late April 2025, giving us more than 3 months to present, and we did receive a CVE ID. It's currently in the reserved but public state. After this presentation becomes public, there will be more information on it. But additionally, we decided also not to name the company or the product here. So my name is Carson. I am a current master's student at Colorado State University studying systems engineering, and I have my bachelor's in electrical engineering.
Hi, I'm Rick. I'm a current PhD student in systems engineering at Colorado State. I got my bachelor's in computer science and then my master's in systems. Both of us work for Dr. Jeremy Daly, who is an associate professor in our department at Colorado State. We work for the System Cyber Research Lab, located at the Powerhouse Energy campus at Colorado State, and our main research focus areas are critical infrastructure, embedded cybersecurity. We do a lot of work on commercial vehicle cybersecurity. We presented at the main stage last year on that. We have a big truck, as you can see, and we get to take that out on fun rides in the airport during all the snow that Fort Collins gets. And we build out a lot of electronics as well. So we do a lot of truck research, so why suddenly investigate boats? Well, I do have a theory. So our advisor got a boat and took it out on the water with us. Carson was water skiing, fell off the boat, decided to hack an autopilot.
And meanwhile, Rick was too afraid to even get in the water, so.
Well, on a more serious note though, boats and marine systems are used in a wide variety of industries. It's important for transportation, shipping, and in military applications. There's also hobbies and entertainment as well, some search and rescue. And in some ways and in some parts, they are part of critical infrastructure. In some parts, they aren't. To dig a deep more into boats, we are familiar very much with CAN and J1939, and boats have NMEA 2000 networks, so that similarity kind of drew us in. And a lot of boats nowadays do use autopilots for maintaining heading, controlling the rudder, and interfacing with GPS and other stuff. So that was one of the main reasons why I decided to get into boats and start looking at them in the first place. Well, before we dive into how we got the autopilot hacked, we want to give everyone a basic 101 on controller area networks. So although the application layer is still NMEA 2000, most boats still use the physical CAN network, like right beneath the NMEA 2000. So what is CAN? Well, basically it's a two-wire network that has a bunch of embedded computers on it. We also call them electronic control units or ECUs. The two wires work on differential signaling and really works well for harsh environments. It's message-based and does arbitration to avoid conflicts. It's very reliable, and that's why it's probably used in a lot of different industries and applications. Cars use them, trucks use them, industrial control systems use them, and also marine systems. So part of the vulnerability that we are going to discuss is called an address claim attack. Address claiming is a very routine procedure in controller area networks and in application layers above that. So basically, whenever a new device or a node joins the network, it has to have a source address, usually from 0 to 253. And this is resolved through an address claim message. So if you can look at the diagram on your right of the screen, whenever a new device comes into the network, it just sends out an address claim message with a name in the data field. Now, most conflicts in address claiming are resolved through name priority. That is, the lower the value of the name field, that wins. So say, for example, there are two controllers trying to claim the address 0. The name priority basically decides who gets to use that address 0. There is no authentication, so essentially, you can steal someone else's address. And that's what we show in the diagram, is what we did here. Like, say, for example, the engine comes in, normal startup, claims address 0, and now starts using address 0 for sending out all the messages. Then after some time, there is a malicious autopilot node that comes in, and it claims address 0 with a lower value in the name field. And then the engine is basically thrown off the network because it can no longer use address 0, and everyone else recognizes the engine through address 0. And that's a classic example of what an address claim attack is. Anyway, moving on.
So the overall motivation of our work, obviously we look into cyber-physical systems, but oftentimes people see boats, trucks as air-gapped. In reality, this is not really the case. As they become more modernized, there's more wireless links to them. But a lot of recent exploits have shown that cyber-physical systems, such as trucks and boats and other critical infrastructure, they are vulnerable to different forms of external control. And this is also seen as a pretty big target for other nations, other groups, whatever they may be. So our goal as researchers is to improve and harden these systems through discovering vulnerabilities, reporting them properly, and ideally helping secure these devices. So this is what a typical marine system architecture may look like. On the left, we have more of a pleasure craft or a yacht. On the right is more of a shipping vessel, for instance. There can be a lot of different devices in there, such as displays, laptops, compasses, autopilots. Your engine is considered a device on the network because it may have a controller associated with it. Obviously, smaller boats are going to be a little bit more simple, but as you get larger, it gets more complex, more things to hack on. So what we did is we wanted to take that and essentially put it into a small box that we have here. So on the photo on the right, we have a chart plotter on the top. This connects up to the Autopilot computer over CAN using the NMEA 2000 protocol. That's what the backbone cable is there for, and a power supply. On the left, we just have a systems diagram showing that you can also plug in via an SD card, for instance, to update things, and you can also plug in with your laptop using a CAN device. So taking a look at the Autopilot hardware itself, this is what the PCB looks like. Some of the first questions that you want to ask when hardware reverse engineering is, how can I update this and how can I connect to it and start reading data, figure out how it works. So we removed it from the enclosure and started looking at the very small part numbers on there. Kind of hard to read using microscopes. Soldering equipment, but ideally we want to locate the data sheets from there, look at the user manuals and the wiring diagrams. So if you notice, I've highlighted something down here. This is a standard connector for the NMEA 2000. This has CAN high and CAN low, power and ground on there, so that was something important to note on there. As we dive in a little bit deeper, we start to understand how the Autopilot works and what features it has. So on the top right, we have a wonderful 20-pin header, which looks pretty interesting. As we dive deeper, we can see that we can send and receive NMEA 2000 frames from this Autopilot. It has the ability to control the steering wheel via a feedback mechanism. It can control the angle of the rudder. And that 20-pin header, we can actually extract the firmware via JTAG and update it as well over the CAN network. So one of the things that we discovered while we were looking up this device and the part numbers is that there is a software update available online through the manufacturer. This was something that we'll cover a little bit later, and then on the right we just have an image of what the memory map looks like for this specific chip architecture. These are very important things when you want to reverse engineer firmware. So we initially plugged in using something called a tie guard. We then switched to a J-Link for more consistency. But what we plugged into is a programming port, which was unfortunately unlocked for us. What we can do with this is extract, modify, and upload firmware to it. We can perform live debugging and also view the registers on the chip live. So now that we have the firmware, this is what a usual high-level overview of software reverse engineering looks like. First, from identifying the binary architecture all the way through locating the patch target. Now, when you get a binary, you don't know what any of this means. It's essentially ones and zeros. So we have to go through and make it a lot more human readable. This takes many hours of us sitting there, scratching our heads, trying to rename functions, trying to figure out which strings map to what. One of the key things that we did was we wanted to send out this address claim. And so we looked for what registers are correlated to the can send function and start remapping and renaming functions in that binary. We used a very popular tool, you might recognize it, to identify the flow and code regions and, as I said, identify the can-related functionality. So we wanted to modify a specific function to do something specific. Now, this is just one example of what you can do, but we wanted to implement this address claim attack, removing the legitimate device from the network and keep it from communicating any further. This ideally demonstrates control over the network. So on the left side, this is what the initial binary looks like. And the highlighted part, this is what the arguments are. It gets passed in a message and data bytes. So we essentially just patch that to be a hard-coded address claim in here just to provide a proof of concept. Once we had those opcodes that we needed to patch the firmware, we actually had to upload it back into that file that we can access online. The file name is a swup, or software update. It's really just an S record encoded into an XML format. Luckily, Wikipedia has a lot of information on S records, which helped us figure out how to do all the checksums and what all the headers mean for each line. After we patch the file, we then can save this to an SD card, at which point we go back to what we saw earlier. We're inserting the SD card into this chart plotter, navigate to the file that we want to upload, and select the target device. Click Upgrade. And so what we get again now is the software update being sent over the network without any authentication, only that checksum there. The autopilot takes this and then reboots and then starts sending out address claims. And this can be nefarious if used improperly. But ideally, this is hacked. Right, we've demonstrated that we can send arbitrary messages from the autopilot. Now, this is, again, just one example, but it's not limited to address claim messages. We could be sending out different GPS commands. We could be sending out other commands to control various other parts of a marine network.
So essentially, at this point, we have gained two important things. One is remote code execution on the autopilot, and that leading to arbitrary can injection with any targeted messages. And that could be used by a nefarious actor, honestly, to gain control over the NMEA network, and also control of physical actuators through the autopilot even. Well, there is some physical access involved in this, but as marine systems keep getting bigger and bigger and there is more IoT devices being plugged into marine systems, a lot of these devices also have Wi-Fi networks, which is something which is interesting. So it'll be interesting to see what other things can be done and how, or whether or not this can be done totally wirelessly without even needing a chart plotter in the first place. So to conclude our presentation, basically what we want to say out loud to the entire community and the maritime community is we need to follow good software practices, sign firmware, disable JTAGs in production, possibly encrypt firmware, maybe remove identifiers from PCB components in production, go through a secure boot process during power up, and so forth. With that ends our presentation. However, we do also have a demo, and we are planning to show the entire thing live to you guys if you are patient for a couple of minutes with us.
No step out. Let reach. Sorry.
Let reach. Unfortunately, we don't have an HDMI for the chart plotter, but if you can see our setup up here, you are even welcome to come up to see this around the stage.
Sorry, just got a question.
Yeah, sure.
People are going to come up there, but how pervasive is this tech on like massive ships and stuff like that?
Well, to be honest, different boards have different architectures.
Yeah.
But however, from what I know, autopilots are present on a lot of larger vessels as well.
Right.
They may operate a lot different, but it
Yeah.
depends on what
Yeah.
protocols they're using.
The big boats also won't be using it in the NMEA 2000.
Oh, people are making that.
So what we have here is a chart plotter, the autopilot, and an actual engine controller that we are going to claim the address of.
I navigate to that firmware updates from the SD card on here.
Is it not showing up? There you go. I have.
Right. So we have normal messages coming across the network right now. So I'm going to go ahead and select that malicious upgrade file. And I'm going to select the device that I want to upgrade with it. And click Start Upgrade. Now this is sending out this upgrade to the autopilot, which is down here. There's not really any authentication process. It's being sent in plain text as well. So a simple capture and replay would also work to upgrade the autopilot.
Fortunately, this is not working out here.
It is by wire over the NMEA 2000 network.
So actually, if you have a license to the pad, you can easily upgrade.
Yeah, unfortunately, this server out here is not working for some reason, and that's what happens when you try to give live demos. Well, what we are going to do is simply look at the CAN dump. That's the update being sent out from the autopilot right there. Yeah.
Do you know how many like hybrid devices which are both CAN and Wi-Fi?
There's some aftermarket devices that you can purchase, just like Auto Electronics. I myself am not familiar with standard devices that have that on there. We usually just purchase random things off the internet.
Like I noticed that Carson, they sell a control system for the chart plotter, and that integrates with the smart ones that they make. They make some of the optics, smartwatches. And you can control the 12-ring motor state from your wrist. So you can do that. A doll, I would find kind of like I asked the doll try to integrate this with anything that can connect any kind of Wi-Fi or remote like that. To see if you can, cause a similar effect without directly getting on the CAN network.
Yeah, there's actually another student in our lab sitting right here that has looked at something like that. Obviously, we need to look into it a little bit more, but there are devices out there that can interface between the two.
Well, on a nicer note, this simulator is now working. You can see the engine controller is active on there.
So there's a source ID of 00 on the right side that you'll see. And then once we start sending out the data frames with a lot of zeros on the right-hand side, you'll notice that the engine actually gets kicked off the network. Should be right about now.
And it's gone. So you're seeing a bunch of address claim messages. So what this allows is basically the engine. Sorry about that. Looks like our timer is almost over. We have 20 minutes on the clock. But that's what it allows us to do. It kicks the engine off the network. And at this point, like if there are other controllers on the network that are trying to send out messages to the engine will not receive it. So say, for example, your brake is trying to tell this is a typical truck scenario example though, but when you're driving a big rig, your brake tells your engine to slow down. it tells your transmission to slow down. Essentially, the engine can't hear any of those messages anymore with an address claim. With that, we would like to conclude our presentation. Thank you. And if you have any questions, please go ahead.